right. So again, this one, right? It's another example. So here we're subtracting. Now notice here that the denominators, they're not factored. Okay? So we have to factor them. No big deal. So let's factor them. So the x squared minus 9, right? Well, that's going to be, as we've seen before, that's just x minus 3 times x plus 3. That's all it is. X minus 3, excuse me, I left something. There we go. X minus 3 times x plus 3. Now for the other one, the x squared minus 8x plus 15. Again, here we have a trinomial, right? Degree 2, leading coefficient 1. So we want two numbers whose product is the constant term. The sum is the coefficient of x, as you can see. So we want two numbers whose product is 15. The sum is negative 8. And hopefully it doesn't take long to see, even before looking at the slide, that negative 5 and negative 3 pull that off. So this becomes this. Okay, so now the denominators have been factored. What are the irreducible factors? X minus 3, x plus 3, and x minus 5. X minus 3 is already listed. Do we list it again? No. So we have those. And you can see that the exponent of each factor is 1, right? So the greatest exponent of each is 1. If we had x minus 3 to a higher power than 1, like 2, 3, or whatever, that would be the biggest exponent. But it's all 1. So our LCD is just this, as you can see. X minus 5 times x plus 3 times x minus 3. You can really multiply in any order because remember, multiplication is commutative. Now, so what do we do next? Well, we know what the LCD is. We also factored the denominators, right? As you can see. So we have to manipulate each one here, each rational expression, so the denominators are the same. Okay, that's not too bad. For the first one, for instance, right? First one here, we're missing x minus 5. So we multiplied bottom and top by that. Here, same idea. We multiplied bottom and top by what's missing to make the denominator the LCD. Right? We have x plus 3, as you can see, is what we're missing. So we multiply that, but we do the same to the top, and we get this. Oh, that's great. That's good. Good. So now we actually subtract, right? And this is what we're doing, right? The denominators don't change. They're the same, right? And now we FOIL the top. So we have 3x minus 15x, excuse me, 3x squared minus 15x. Again, for the second product, I used parentheses. I would use parentheses, that is. And why is that? Because again, you want to distribute this negative. If you don't distribute that negative, you're not going to get the right answer. I can tell you that right now. So from here, what we get is this. Right? 9x minus 5x, that's just 4x. So I guess now we distribute the minus sign. So from here, we get this. The 3x squares cancel. and we get this. And hopefully you can see that this is going to be simplified. I mean, the numerator is factored, so is the denominator, right? And they clearly have no common factors. So the answer is already simplified. All right. Are there any questions about this? Remember, I can't see the chat, so if you have a question, use that, what do you call it, the hand raise feature. Okay, so let me at least begin a chapter 8. So I'm gonna minimize this. Let me get the chapter 8 notes up. If I can, there it is. And again, we're not going to do all of chapter 8. Although I am going to try and do more than I usually do, since we have time. Okay. Since we have some time before the semester ends, we have this week and the week after break. So not next, so we have this week, next week we're off, but the following week, we have as well. All right, so this is chapter 8. I did send this to everyone. Basically here, what we're gonna look at is a system of equations. We're gonna see what that is. That is, as you can see, we're gonna see what a system of equations, like what it is, we'll see the definition. We're really going to focus, though, on linear equations. In other words, when the variables, their exponents are 1. Kind of like what we did in section 1.1, if I remember correctly. We're going to see what a system of linear equations is. We're going to see 3 different ways to solve it. In the past, when I taught this in class, what I would do is only do substitution and graphically for time consideration. But I want to try and get through elimination as well. I think most students have seen that before. If you haven't, that's okay though. But we're going to see 3 different ways of solving it though. Okay, now math is like any other science, right? So there is going to be some terminology, and that's what we have here. So we have basically here what a system of equations, what it is. Any collection of equations in the same variables, that's a system of equations. So the equations have to be in the same variables. They all have to be in x, they all have to be in y, they all have to be in x and y, that kind of thing. And what we're going to deal with is something that looks like this. As you can see. Basically here, A, B, C, D, J, K, they're going to be real numbers. What has to happen, though, is you can't have A and B be 0 at the same time. Same thing with D and J. If A and B are both 0, you really only have one equation then. They were back in section 1.1. Same thing with D and J. You want D and J to be non-zero. At least one of them has to be non-zero. So as you can see, we're taking what we've seen earlier, like in chapter 1, for instance, and we're kicking it up a notch, so to say. We're not looking at just one, we're looking at 2 equations. I know also in the course description, they talk about matrices. One can actually use a matrix to solve this. I'm not going to go into that too much, though, if at all. So just letting you know. When they say matrices, one can use that to solve this. What do I mean by solve, though? Well, we're looking for solutions. Well, what is a solution? A solution to this system, to a system like this, it's a solution to both of these equations. So in other words, remember, if you have an equation in x and y, right, your solution is going to be an ordered pair, not just a number. Since we have two variables, we're not looking, our solutions will be ordered pairs of real numbers. But a solution to a system like this, it's an ordered pair that is a solution to both of these equations. So it's a solution to the first equation and it's a solution to the second equation. Again, that's just a definition. Now you might be concerned actually where, oh my goodness, how many solutions can there be, right? Well, it turns out there's only 3 possibilities. Okay, so I forgot about this slide. But here I'm just demonstrating that 3(1) is a solution to this system. What I just said actually is going to be on the next slide. But this is just showing it's a solution to this system because it's a solution to both equations. I'll probably start from here next time because we're almost out of time. But let me just show you quickly. It turns out there's only 3 possibilities concerning the number of solutions. There's either no solutions, exactly 1, or infinitely many. So what I will do though is I'll start from this slide next time. So why don't we stop here? Because we're out of time. All right.